Welcome students to the 6th lecture on fuzzy sets, arithmetic and logic. In this lecture, we shall primarily study T-conorms or fuzzy union. We shall investigate their properties and also we will look at how to combine different operators. We know if A is a fuzzy set, defined over a universe U and B is another fuzzy set on U, then for x belonging to U, we need to define the membership of x to the fuzzy set A union B, that is which is a function of mu A x, membership of x in A and membership of x to the set B. The standard union, as we have seen, earlier, is maximum of mu A x and mu B x. But just like complement and intersection, here also we can think of generalization. So, the generalization comes in the following way. We define function U from 0, 1 cross 0, 1 to 0, 1 such that if the inputs are mu A x and mu B x, the output will be mu A union B x. Obviously, every arbitrary function defined from 0 to 1 cross 0 to 1 mapping into the real interval 0 1 is not a union function. We need to understand the properties that a fuzzy T-conorm or fuzzy union function should have. So, we enlist some of these properties which are called axioms. 1. The first thing is that it is a boundary condition. Union of a comma 0 is equal to a. That means, if x has membership A small a to the set capital A, but x membership to the set capital B is 0, then membership of x to the union of A and B should also be A. If we understand that, then we go to the second property, which is called monotonicity. What is that? If B is less than equal to D, then union of A B is less than equal to union of A D. Commutative or commutativity property, that means u of A B is same as u of B A. And number 4 is associativity. Union of A comma union of B comma D is equal to union of A comma B comma D. These properties, if you notice, are very similar to the properties of intersection that we have seen in the earlier lecture, but of course, there are certain desirable properties. U is continuous as explained with respect to complementation and intersection, otherwise small change in the membership may result in significant change in the membership of the union. U A should be greater than A. This is obvious. This is very natural, since u A comma 0 equal to A, one would expect that if the membership to the second set is bigger than 0, then membership value to the union should be more. Therefore, since here we are looking at the second membership value as A instead of 0, it is expected that the membership to the union will be greater than A. If A1 less than A2 and B1 less than B2, then union over A1 comma B1 is less than union over A2 comma B2, and this we have seen is very similar to what we have done with respect to intersection. We have seen a theorem with respect to intersection. So, a similar theorem we write with respect to union, show that the standard union that is U A B is equal to max of A comma B is the only idempotent conorm. Leave it as an exercise. Very similar to the corresponding theorem for intersection or T-norms. As before, some common union functions are standard, that is U of A B is equal to max of A B. We will write it as U M, algebraic sum. If you remember, for intersection it was product. Here the function is U A B is equal to A plus B minus A B. We will write it as U A bounded sum, again very similar to the bounded product that we have seen with respect to intersection. And finally, let us write drastic union, that is U A B is equal to A if B is equal to 0 is equal to B if A is equal to 0 and it is equal to 1 otherwise. That is, if any one of them is 0, then the membership to the union is the value of membership of the other one, but if both of them are non-zero, then it does not matter, we are giving full membership to the union. Again, one result that I want you to prove is this: prove that for any arbitrary conorm U, max A comma B, that is the standard union, is less than equal to that is the drastic union. So, very similar result we have seen with respect to fuzzy T-norms. I want you to emulate that proof to prove this statement. This result tells us that standard union is the smallest of all unions and drastic union is the largest of all conorms. Combination of operators with respect to crisp sets we have De Morgan's law. That is A intersection B complement is equal to A complement union B complement and A union B complement is equal to A complement intersection B complement. We need to investigate the validity of the above laws with respect to generalized operators. Or operations. So, when we look at the laws with respect to fuzzy sets, we write them as follows. A intersection B complement, we write it as C of I of A comma B, A union B complement is equal to C of U of A comma B, and we want to check if C of I of A comma B is equal to union of the complement of A and complement of B, and if the C of union of A comma B is equal to intersection of complement of A comma complement of B. Any triplet C I U where C is a complementation function, I is an intersection function and U is a union function that satisfies the above two laws are called dual triplet. Result. All the 4 types of T-norms and corresponding T-conorms are dual triplets with respect to the standard complement function C of A is equal to 1 minus A. So, let us verify. Okay, verification. Let us first verify it when we use standard union that is max, standard intersection, that is mean, and of course, standard complement that is C of A is equal to 1 minus A. De Morgan's laws are A union B complement is equal to A complement intersection B complement. That is, with our notation, complement of union of A comma B is equal to intersection of complement of A comma complement of B. Now, C of U of A B is equal to 1 minus U of A B is equal to 1 minus maximum of A comma B is equal to minimum of 1 minus A comma 1 minus B, which is equal to minimum of complement of A and complement of B, and since it is mean, it is the standard intersection of complement of A and complement of B, which is effectively A complement intersection B complement. Conversely, A complement intersection B complement, we can write it as I
C of A comma C of B is equal to minimum of C of A comma C of B is equal to minimum of 1 minus A comma 1 minus B is equal to 1 minus maximum of A comma B is equal to 1 minus union of A comma B is equal to complement of U A comma B, which is equal to A union B complement. So, this establishes the first law. The second law is A intersection B complement is equal to A complement union B complement. So, this we write as C of I of A comma B is equal to 1 minus I of A comma B is equal to 1 minus minimum of A comma B is equal to maximum of 1 minus A comma 1 minus B is equal to union of complement of A comma complement of B. Therefore, we establish that A intersection B complement is actually union of complement of A and complement of B. Conversely, A complement union B complement, we can write it as union of complement of A comma complement of B is equal to maximum of 1 minus A comma 1 minus B is equal to 1 minus minimum of A comma B is equal to complement of intersection of A comma B, that is, this is A intersection B complement. So, this verifies our statement with respect to standard union and standard intersection. We shall now verify with respect to some other union and intersection function.
Let us verify the same with respect to algebraic sum product that is whether C comma minimum is A B, that is the algebraic product, that is the intersection, and union is equal to A plus B minus A B. Therefore, we want to check whether this triplet is a dual triplet. Mind you, C is the standard complement. Therefore, C of I of A comma B is equal to C of A B is equal to 1 minus A B is equal to 1 minus A plus 1 minus B minus 1 minus A into 1 minus B. This we can verify easily, because this is equal to 1 minus A plus 1 minus B minus the product of this, which is 1 minus A minus B plus A B is equal to, one of these plus 1s is cancelled with this minus 1. This minus A cancels with this, because there is a negative sign. This minus B cancels with this, because there is the negative sign, and this minus 1 cancels with this. What is left is 1 minus A B. Therefore, C of I of A comma B can be written as this, which is nothing but complement of A plus complement of B minus complement of A into complement of B, and which is nothing but union of complement of A comma complement of B. Similarly, complement of U of A comma B is equal to 1 minus union of A comma B is A plus B minus A B is equal to 1 minus A minus B plus A B is equal to 1 minus A minus B into 1 minus A is equal to 1 minus A into 1 minus B. Therefore, this is nothing but intersection of complement of A comma complement of B, because under algebraic product and sum, complement comes as the product of the two terms. I like you to verify the same results with respect to the other two types of union and intersections that we have mentioned, namely bounded sum and product and drastic. Theorem: C comma mean comma max and C comma drastic intersection and drastic union are dual triplets with respect to any arbitrary complement function C. Proof: consider C mean max. Let, without loss of generality, A less than B. Therefore, C of mean of A B is equal to, since A is less than B, is same as C of A is equal to maximum of C of A and C of B, since if A less than B, then complement of A is greater than complement of B. Similarly, C of maximum of A comma B is equal to C of B, since A is less than B, is equal to minimum of C of A and C of B, since C of A is greater than C of B. Therefore, the results are verified for standard union and intersection with respect to any arbitrary complement function C. I suggest that you verify the same results with respect to drastic union and intersection. Now, let us consider the triplet drastic intersection, drastic union and any arbitrary complement C. What is drastic? Let me recollect. Drastic of A comma B intersection is equal to A if B is equal to 1, B if A is equal to 1 and 0 otherwise. And when you look at drastic union, A comma B is A if B is equal to 0, B if A is equal to 0 and 1 otherwise. Case 1, 0 less than A comma B less than 1. That is, both A comma B are less than 1. Therefore, C drastic intersection of A comma B is equal to, since both are less than 1, we get 0 is equal to C of 0 is equal to 1. And drastic union of C of A and C of B is equal to, since neither of A and B is 1 or 0, this is not equal to 0, this is not equal to 0. Therefore, by definition of drastic union, this is 1. Therefore, we see that C of U D A comma B is equal to 1 is equal to U D of C of A comma C of B. Case 2, at least one of A comma B is 1 without loss of generality. Let us assume A is equal to 1. Therefore, C of drastic intersection of A comma B is equal to, since A is equal to 1, intersection of A comma B is B, is equal to C of B, and drastic union of C of A comma C of B is equal to drastic union of 0 comma C B, and by definition complement of B. I request you show that it holds for C of U d of A comma B is equal to I leave that as an exercise. The question comes, therefore, how do we know or how do we construct a dual triplet? The following theorem helps us in designing that. When we have a T norm and we have an involutive complement function, then we can construct a T-conorm with the help of them in the following way, and not only that, the newly constructed T-conorm is actually will be forming a dual triplet with respect to the T norm and the complement function. So, the theorem is like that. Let I star be any T norm and C be any involutive complement function, then we can construct a T-conorm U star as follows. U star of A B is equal to complement of I star of complement of A comma complement of B, and the triplet C I star U star is a dual triplet. First, we show that U star is indeed a T-conorm. For that, we need to verify the 4 necessary properties. U star of a comma 0 is equal to a. We know that it is the boundary condition. We have U star of a 0 is equal to C of I star of C of a comma C of 0 is equal to C of I star of C of a comma 1 is equal to C of a, since I star is a T-norm, and therefore, by its axioms I star of a comma 1 is equal to a, that is the boundary condition, is equal to C of a is equal to a, since C is involutive. Therefore, property 1 is verified. 2. Monotonicity. We need to show that U star of a comma b is less than equal to U star of a comma d if b is less than d. Since C is a complement, and b is less than d, we have C of b is greater than equal to C of d. Therefore, I star of C of a comma C of b is greater than equal to I star of C of a comma C of d. This is because of monotonicity of I star. Therefore, C of I star of C of a comma C of b is less than equal to C of I star of C of a comma C of d. Because we are now taking the complements, therefore, inequalities will be reversed, and this is nothing but U star of a comma b, and this is nothing but U star of a comma d. Therefore, we get that U star of a comma b is less than equal to U star of a comma d. third property, commutative, that is u star of a comma b is equal to u star of b comma a. This is obvious since u star of a b is equal to C of I star of C of A comma C of B is equal to C of I star of C of B comma C of A, because I star is commutative is equal to u star of B comma A. The fourth property is associativity, that is u star of A comma u star of B comma D is equal to u star of A comma B comma D. I leave this as an exercise and I want you to apply the definition of U star and different properties of I and C to verify this result. Before I stop today, I state and prove another theorem. Let C I U be a dual triplet that satisfies law of excluded middle and law of contradiction. Then the triple does not satisfy the distributive laws that is A union B intersection C is equal to A union B intersection with A union C and A intersection B union C is equal to A intersection C union B union A intersection C. So, the theorem suggests that if I and U are norms, T norms and T conorms such that along with C, which is a complement function, it satisfies the law of excluded middle and law of contradiction, then this distributive property does not hold. Now, the law of excluded middle is A union A complement is equal to U, the universe, and law of contradiction implies A intersection with A complement is equal to phi. When we write with respect to T-norms and T-conorms, we have u of A comma C of A is equal to 1, which is the law of excluded middle, and I of A and C of A is equal to 0, law of contradiction. So, to write the distributive laws using C comma I and U, we have A intersection B union D is equal to A intersection B union A intersection D. That is, I of A comma union of B comma D is equal to I of A comma B, I of A comma D, and the union function is applied over them. So, let us assume we need to show that this does not hold. So, let us assume that the above law holds. Let E be the equilibrium of C. Note that E is an equilibrium implies C of E is equal to E. Therefore, E is not equal to 0 and E not equal to 1. Therefore, E lies between the interval 0 to 1, open interval. Therefore, U of E E is equal to U of E comma C, because C is same as E, is equal to 1. By law of excluded middle. And I of E comma E is equal to I of E comma C is equal to 0 by law of contradiction. Therefore, when we use the distributive law on E, we have I of E comma union of E comma E is equal to union of I of E comma E comma I of E comma E implies I of E comma 1, since U E is equal to 1 is equal to union of 0 comma 0, since I E is equal to 0. Just now I have proved. Therefore, this implies that 1 is equal to 0. This is a contradiction. Therefore, if we assume that the distributive law holds, we arrive at a contradiction. Very similar contradiction we will get if we consider the other distributive law, that is, apply a similar technique to show that U A I B comma D equal to I of U of A comma B comma U of A comma D also does not hold. I leave that as an exercise. Okay, student, I stop here today. So, in this set of 3 lectures, we had looked at different set operations, their properties and certain properties related to combining them. Now, I will change the topic, and from the next class I will start fuzzy arithmetic, that is arithmetic using fuzzy numbers. Thank you so much.